Everybody thinks they know that randomised controlled trials are a really good thing. They are the gold standard in medicine. They're what we do if we want to find out if a treatment is better or worse than nothing, better or worse than what we already have. And the design is very simple. So let's say you've got a bunch of people with horrible headache. You take 200 people with horrible headache, you split them in half at random, half of them take your fantastic whiz-bang new headache drug, half of them take a dummy placebo sugar pill that contains no medicine, and then an hour later you get them to fill out a little form maybe, giving how bad their headache is on a scale of 1 to 10, and you look and see if the people who've got your fantastic headache treatment have got better headache symptoms than the people who are getting your old dummy placebo sugar pill or your old cheap treatment for headache. Everybody gets that, right? You're smiling, you know about that stuff. But there's a problem, because not all trials are alike. Trials can be flawed by design in such a way that they are no longer fair tests of which treatment is best. And so, what I'm going to do is whiz through my kind of favourite top 10 examples of how trial designs can be rigged. We were talking about methodological flaws in clinical trials. So, here is a list of the stuff we're going to go through. We're going to go through dodgy comparators, comparing things with other treatments that aren't very good in order to make your new treatment look fabulous. People switching primary outcomes, dodgy subgroup analyses, missing data, weird patients, silly outcomes, trials that are too small, trials that are subject to fraud, spin, and seeding trials. So, first, okay, we all think that we know that the best design, amateurs think that the best design of a randomised controlled trial is you compare your fabulous new treatment against a dummy placebo sugar pill that contains no medicine. And that's true if you've got a very low bar. Right? It's true of, for example, trials of homeopathy, because we know that basically homeopathy doesn't work. So, you know, we're willing to say if you can do better than nothing, then fine. You know, that's scientifically interesting, even though it's probably still not very effective. But for most of the interesting treatment questions in medicine, we don't care whether your new treatment is better than nothing, because we've already got something. We're interested in whether your new treatment is better than the treatment we already have. We're interested in whether your new treatment is better than the best currently available treatment. Now, that is called comparative effectiveness research. And in the extraordinary, peculiar world of American healthcare, comparative effectiveness research is like a kind of a dirty word for big sections of industry. It's like socialized medicine and death panels, right? They think it's a strange and appalling and ludicrous idea, but actually it's a very straightforward idea. We don't care whether your treatment's better than nothing. We want to know which is the best treatment because we want to give the best treatment to our patients. And yet, when you look across all of the new treatments approved by the FDA from 2000 to 2010, and this is a JAMA paper from 2011, only 70% of 70% of new FDA approvals only compared the new treatment against a dummy placebo sugar pill. So overwhelmingly, treatments are being approved that have only been compared against nothing. Now, here we come up against a really important issue, which has become very salient just recently with the new evidence and the 2 new papers published this week in the British Medical Journal showing that the FDA's threshold for approving new treatments seems to be going down. They seem to be becoming more permissive. Because actually, should it matter? It's a really interesting question. Just because a drug is on the market, just because it's available for prescription by doctors, that doesn't mean that it necessarily is the drug that you should give to your patient. And equally, it doesn't mean that as a patient, it is the drug that you should naturally want to take. I think it's actually quite okay for there to be a very low bar for new treatments being approved onto the market, because when you're making a decision as a regulator, you're saying, look, is there ever going to be a situation in which even a handful of people might want to use this treatment? Maybe they have weird idiosyncratic side effects from all of the other better treatments. Maybe they have weird idiosyncratic responses to the other treatments, and they don't do very well on those, but you know, peculiarly enough, they do well on this 5th best drug in its class. I think it's fine, in some respects, for crap drugs to be approved onto the market. But what you then need is secondary and tertiary filters in the system. And those filters need to be informed, judicious consumers, if you like, but really, you know, doctors and patients. and to an extent perhaps nice. People saying, well, it's fine, this drug is out there, it's available strictly legally for prescription, but do we want to use it? And to make that judgment call, you have to critically appraise the evidence. And critically appraising the evidence means looking at the trials and seeing if they're actually any good. So if you see that a drug is approved with only evidence comparing it against a dummy placebo sugar pill, and there are other effective treatments in that class, then we can drive up standards collectively in the medical profession and the patient community and as commissioners of health services by saying, well, it's great that you've got your drug on the market, but clearly we're not really going to use it until you do good quality, large trials, measuring real-world outcomes, comparing it against the best currently available treatment. So, comparing your drug against a dummy placebo sugar pill is one way of making it look good, because it's very easy to look better than nothing. Another interesting trick is to compare it against the competing drug in sometimes perhaps too low a dose. So you make your drug look fantastic because the people on the other competing treatment are being undertreated. Or to compare it against the competing drug, if side effects are important, in a trial where you give the competing drug in too high a dose so that people get nasty side effects. Now you might think this is ludicrous conspiracy theory and appalling, so here are some interesting examples. Firstly, the history of antipsychotic medication is a really fascinating and interesting one. It's got a lot in common actually, I think, with cancer treatments and chemotherapy. Schizophrenia is a horrible, terrible, destructive, chronic disease that ruins lives, although people can live well and live productively and live happily for many, many decades. The treatments that we have for schizophrenia have some benefits, they have some positive effects, but they also have very unpleasant side effects. They induce, for example, Parkinsonism, so odd movement disorders, the kind of thing which in playgrounds, I remember as a kid, people would mock, because I grew up in Oxford, and we would see people walking up to Littlemore, and, you know, Littlemore was a term of abuse. It's horrible, the way that children talk. And people would mimic the movement disorders that patients with schizophrenia had. Now, those movement disorders are partly a consequence of the disease itself, but they are more a consequence of the treatments that people are given. Now, that's not to say that those are bad treatments. It's to say that you have to weigh up benefits and adverse effects. Now, in the 1980s, a few decades ago, there was this great new horizon in the treatment of schizophrenia, which was the new generation antipsychotic drugs. And the promise of these drugs was not so much that they were better at treating schizophrenia, but rather it was that they had fewer side effects. And so people set about trying to do trials to examine the relative side effects for people getting the new drugs versus people getting the old drugs. So here are 8 such trials comparing atypical neuroleptics, these are medical student slides, which is why they're full of annoying words like that, new generation antipsychotics versus old-fashioned haloperidol. So first up, 5 trials comparing fabulous whiz-bang new generation antipsychotics, which you hope are going to have fewer side effects, against haloperidol at a fixed dose of... Are there any psychiatrists in the audience today by any chance? No? Anybody who's a GP? No? Okay. So a fixed dose of 20 milligrams a day. In an environment of psychiatrists, that would solicit lols, right? So 20 milligrams a day of haloperidol, it's not a criminally high dose. It's not going to get you immediately struck off if you give it to your patients, sometimes, but it is an unusually high dose of haloperidol. It's at the higher end of what's permitted in the BNF, and it is a foregone conclusion that if you're giving your patients an unusually high dose of haloperidol like that, that they are likely to experience more side effects. And so you will inevitably make your new drug look like it has fewer side effects than haloperidol. And then similarly, there are 2 other trials where people were allowed to pick their own dose of haloperidol as they went, the clinicians, and yet somehow mysteriously they all seemed to select doses of greater than 20 milligrams a day. Now, I don't know that these studies were definitely being conducted by people who were attempting to rig it, but I think that these are odd doses, and I think that is worthy of discussion. Interestingly, history kind of repeated itself a few years later. So when you develop a drug and you bring it to market, it's yours, you own it alone, generally for about a decade after it gets to market, and then it enters the public domain. So it becomes like Happy Birthday just has. Like we're all allowed to sing Happy Birthday now in Hollywood movies without paying big copyright fees to Warner. Similarly, we're all allowed to manufacture aspirin or ibuprofen if we wish to. And so that's why It's very cheap. You can buy a crate of ibuprofen for a couple of quid from Lidl. Now, once your drug comes off patent, comes out of copyright, if you like, then it becomes very cheap, and other people can make copies of it. So, risperidone was pretty much the first of the new generation antipsychotics that was being widely used. But in the mid-90s, it started coming up to being out of copyright. And so suddenly people wanted to say, well, actually, our new generation antipsychotics is much better this time than risperidone. So they weren't trying to make their drugs look better than really old-fashioned antipsychotics. They were trying to make it look better than risperidone suddenly. So now you see trials, and by the way, these come from an excellent review of Bad Trial Design by Daniel Safer from a couple of years ago. Suddenly you see trials of new generation antipsychotics being compared against risperidone in fixed or average doses. Okay, so you need a bit of background data for the lol. So risperidone, you would probably start on maybe 1 or 2 milligrams a day, probably split doses because blood pressure drops. You reasonably expect to go to 4. Sometimes you go to 6, possibly 8. 8's a pretty high dose of risperidone, really, and you can't go much higher than that in the BNF. And by the time you start going really high with risperidone, sometimes you find that you're lactating, and all kinds of odd side effects can come about with risperidone. That's not to say it's a bad drug. That's just to say these are things that you need to bear in mind, and also that adverse events are dose responsive. So, a bunch of trials comparing new generation antipsychotics against risperidone in fixed or average doses of 7.28 milligrams a day. So again, not appalling, not criminal, you're not going to get struck off, but just oddly high doses. Next! Oh, sorry, this is I was updating these slides, and that's like a placeholder for a story I was going to insert, but haven't. So there you go. Right, the next thing you can do, if you want to rig your trial in such a way that it gives you a flattering answer, is you can switch the main outcome. So I guess you're all familiar, there's a kind of game that you play, that people do on kind of seafronts, where there's 3 cups and 1 ball, and you put the ball under the cup, and then the person goes, and they whiz it around, right? And then they go, okay, guess which cup the ball, which cup the ball is under. And the deal is you put down £5, and if you correctly guess which cup has the ball, you get back £15, right? Because there are 3 cups. You're allowed to look under 1, right? We all understand there's basic odds, right? Are you allowed to look under 2 cups? No. Why are you not allowed to look under 2 cups? Well, if you looked under 2 cups, assuming it's completely random which cup has the ball underneath it, if you looked under 2 cups, then you're cheating because you're giving yourself a 2 out of 3 chance of finding the ball rather than a 1 out of 3 chance of finding the ball. Does pretty much, I mean, everyone gets that, right? You understand why you're not allowed to look under more than 1 cup, yes? Fine. So, it's kind of peculiar that journal editors and regulators don't get that. Because you see exactly the same problem in clinical trials. Let's say you're doing a clinical trial of a new antidepressant. So you're not just measuring one outcome, right? You're not just measuring depressed or not as a binary variable, yes or no. If you're doing a trial of antidepressant, you could very easily get to the point where you're measuring 20 different outcomes. You might go, well, I'm going to measure, overall mental well-being using the Beck Depression Inventory. I'll also use the anxiety and depression subscales of the Beck Depression Inventory. I'll use the Hamilton Anxiety and Depression Scale because that's interesting and it's different and it's been validated in different populations. And also I'll use the anxiety and depression subscales of the HAM-D as well. Actually, I'm going to use the long version and the short version of the HAM-D. I'm going to do a PHQ-9, which is a really good screening tool for depression, just so that my results are externally comparable to GPs who collect PHQ-9 quite a lot. I'll do maybe a back-to-work questionnaire, because actually, returning to normal function is kind of important, and a quality-of-life questionnaire. I'll do an 8-point scale quality-of-life questionnaire, and I'll do a really good 50-point scale quality-of-life questionnaire. And before you know it, you're measuring 20 different things. Now, if you're measuring 20 different things, those are all subject to random noise and variation. Sometimes things go up, sometimes things go down. You might find, for example, like the employment outcome in your trial might suddenly go up, even in the group whose misery has also got worse, just because of just the play of chance, right? Maybe a couple of people applied for jobs at the beginning of the trial, didn't get them because they were so depressed and miserable that they performed really badly at the interview, and then maybe the other people for competing for that job dropped out, and so suddenly out of nowhere they get given a job. You know, the other people couldn't take it up. They didn't want to migrate from New Zealand. They couldn't afford to live in Oxford, right? And so they weren't going to live in Whitney, and they fuck that. They were just going to not take the job. This is a problem. So suddenly you find employment goes up in your group that are doing worse just because of kind of random noise in your data. Right? You can see that there's random noise in this kind of data. Okay, so in a trial, you would typically set the cutoff for statistical significance at being a p-value of less than 0.05. Now, fundamentally, unless there are statisticians in the room, that basically means there's a 1 in 20 chance that this could have occurred purely by luck, purely by sort of random play of chance in your data. So, here's the problem. If you measure 20 different outcomes in your trial, then it's pretty much a foregone conclusion that for at least one of them, your new drug is going to look better than the old drug by the end of your trial. If you measure 12 different outcomes, there's a 50-50 chance that your new drug is going to look better than your old drug by the end of your trial. Not because of any actual real benefit of the treatment, but just simply because of the play of chance, simply because you're looking under so many cups that eventually you're going to find the ball, right? Now, does that happen? Well, yes. Study 329 is just in the news this week. Study 329 is probably one of the most notorious trials in psychiatry. It was a trial where it was a trial of paroxetine, Seroxat, maybe known to you, a GSK drug, the focus of some terrible, terrible bad behaviour in research in all kinds of different ways, including serious adverse event data being withheld not just from doctors, researchers and patients, that's business as usual, but also even from regulators, which is extraordinary. And so Study 329 was a classic of the genre of dodgy trial analysis. So in the original protocols, there were 2 main outcomes measured and 6 secondary outcomes measured. So you basically say, you're supposed to say at the beginning of your trial, these are the main things that we're interested in measuring. These are the things we're going to consider to be our primary outcomes, and then here are a few more that are secondary outcomes, but maybe we'll have a higher threshold for considering them to be improved. There was no difference for paroxetine versus placebo for any of those 2 pre-specified primary outcomes or any of the 6 pre-specified secondary outcomes. So this was a trial with a negative result. It showed that the treatment was no better than a dummy placebo, right? A negative result. But when it was published, it turns out they measured 19 more outcomes as they went along. Like I said, you could find yourself measuring a lot of different things in a depression trial. So that's 27 outcomes in total, 27 cups they were allowed to look under if they wanted to try and find the balls. And 4 of those gave a positive result for paroxetine. And those positive findings were reported as if they had been the main outcomes all along. Now you can see that there is a problem with that. And we established at the very beginning, right, that you regard yourselves as reasonably intelligent. I thought I was a bit arrogant, but it's all right, it's nice. No, it's nice. It's good that you're so self-confident. But none of you know anything about clinical research, right? We established you're not nerds, you're not research methodologists, you're not epidemiologists, you're not clinical trialists, none of you are even doctors. You can see that this is absurd. And I haven't misled you in this description. That's a perfectly faithful description of what happened with Study 329. And so isn't it extraordinary that, firstly, the journal permits this, and journals routinely permit outcome switching, even today. And if anybody's interested in doing some work on this, ben@badscience.net, medical students, but in particular, but we're doing some interesting crowdsourced activity on this that will help. You can see that this is foolish. Journal editors permit it, and when it has been pointed out to the journal, they've refused to retract the study, even to this day, over a decade later. The institution have failed to take action, no proper correction. Now, you might say, well, this is one of the most notorious dodgy trials in the history of medical research, so most people who know or care know that Study 329 was broken in this way. But even so, what an extraordinary testament to the flawed information architecture of evidence-based medicine. And also, crucially, this isn't a one-off. So, for example, all of the gabapentin trials up to 2009 were reviewed by Kay Dickerson and a bunch of others in 2009, New England Journal paper, biggest journal in the world, very exciting. Everybody's excited to get in the New England Journal. So they looked at all the trials that have been done on gabapentin up to 2009, where you could see what the primary outcome was pre-specified as being. Half of the primary outcomes were never half of the studies were never published. 12 were. That's business as usual, by the way. There were 21 primary outcomes pre-specified in the protocols. Only 11 of those appeared. 6 weren't reported in any form. 4 were reported as if they were secondary outcomes. Meanwhile, there were 28 primary outcomes that were reported in the 12 published trials, of which about half were completely, just literally pulled out of someone's arse. Isn't that extraordinary? Isn't that truly extraordinary? So this isn't anecdote, this is an overview of all of the trials on one very frequently used treatment. Very difficult to do research on this because people are reluctant often to share the data with you. So this is another really interesting paper by An-Wen Chan, published in JAMA 2004, one of the biggest journals in the world. One thing I find interesting about this is, I did a book called Bad Pharma a couple of years ago, which is really just a sort of howl. There's nothing subversive about it. I'm aggressively perfectionist, right? I just expect that if we're going to say we're practicing evidence-based medicine, we should do that. We should do it properly. We should hold the line. So Bad Pharma is, it's not really about particularly drug companies being dreadful. It's about how ludicrously permissive and amateurish we are in medicine, so the medical profession, the academic profession, the journal editors, the regulators across the board, how we permit all of this to happen. But also, when the book came out, there were sort of people queuing up from industry to say, oh, this is all sort of all in the past, or this is all made up. Actually, it's not. What's interesting is it's all just simply an accessible public description of some very, very well documented and widely discussed methodological problems in research that people talk about all the time. It was really strange. I don't know why I'm sharing this with you, but it was genuinely really strange, having literally just written a pop science book about stuff which professional doctors and researchers all the time are going, oh yeah, there's a problem with outcome switching there, and the population of that trial isn't really representative of the real world population. And then you see the head of the ABPI, the British Pharmaceutical Industry Association, saying, this is ridiculous, this doesn't happen. And you go, this is literally it's a JAMA paper. It's a JAMA paper showing the prevalence of this problem in a representative sample of trials on treatments that are used today. Anyway, I'll shut up. I mean, I won't shut up. I'll move on. I'll stop complaining. So, this is a nice 2004 study. So remember, by the way, in case you're thinking, oh, well, that's 2004, the treatments that we use today are the treatments that came on the market over the past 5, 10, 15, 20 years. If you Google the treatments that you take, it's very unlikely you're going to find they came on the market in January 2015, right? So the methodological shortcomings of the research from 5 years ago, 10 years ago and 15 years ago are extremely relevant to patient care today. So they took all the trials approved by the ethics committees of 2 cities over 2 years. There were 2 cities in Scandinavia. They tried to do it in England, and the ethics committees wouldn't give them the information. Isn't that extraordinary? There you go. About half of the outcomes were incorrectly reported. 2/3 had at least one pre-specified primary outcome that had been switched, and positive outcomes were more than twice as likely to be properly reported compared with negative outcomes. So when people got the finding they wanted, they were happy to go, oh yeah, great, that is here we go, it's a primary outcome. And when they didn't get the finding they wanted, then it disappeared down a rabbit warren. So, highly prevalent problem, unaddressed. Oh, this is interesting. I didn't know that was in there. Okay, so this is just for my own interest. I was just reading through the Lancet, and this is the table 2. This is the main results page from a trial that was in the Lancet. I think it was about May 2005. And I just decided for my own interest, like, let's go through the table 2, the main results page, and compare that against the registry entry. Have I got a slide of that? No. And just sort of let's see how they compare. And it's really interesting. So green means it was a pre-specified primary outcome. Although interestingly, you'll note this is so boring and completely inappropriate for a lay audience. I do apologise for having the wrong slides. So first of all, you'll note, so the intention to treat analysis, that means you don't play fast and loose with missing data, right? You keep it honest with the missing patients. Intention to treat analysis you can see p equals 0.0529, so they're just a shaving off being statistically significant. Now, people who read academic journals are not infantile, right? We're all perfectly capable of going, that's fine, that's borderline statistically significant. Don't feel obliged to do another analysis where you manage to get the p-value down to p equals 0.0479. That's of no value or interest to me. It's not materially different, right? 0.05 is not a hard cutoff. But anyway, that's what they've done. Instead of using Poisson regression, they also analysed it using negative binomial regression and managed to get it to 0.0424. Little round of applause for the researchers there. So that's interesting, and an interesting illustration of the shortcomings in pre-registration, because the pre-specified primary outcome doesn't specify which analytic method is going to be used on the register. Just to be clear, I do recognise this is an inappropriate level of detail. But look, here they've done a little per-protocol analysis. Per-protocol analysis means you go, basically, the people who were lost to follow-up and who didn't take the treatment properly, we just ignore them. And that pretty much always gives you a better result. And there it does. Yep. And then all these highlighted in red, these weren't mentioned anywhere as being pre-specified outcomes at all, and the amber ones are secondary. So this is an ongoing problem, and it's ridiculous that we haven't fixed it. Next, subgroup analyses. Okay, so right, you know, at Christmas, you have Christmas pudding, and the Christmas pudding has some 20p's in it. Or you're all quite old, so in the vampire economics, you probably have pound coins in yours. Right. So you know how you, from an older generation, with your £1 million houses, you in your Christmas pudding you fill it with like gold doubloons and cackle at the housing plight of the young, right? So the deal is on Christmas morning, Christmas Day, you have your pudding, and it's chance, right? Who gets 5 coins? Who gets 1 coin? It's chance, right? And you chop into it, and sometimes you might get 1, sometimes you might get 6. Now, if I X-rayed the Christmas pudding before cutting it, in order to see which bit of the Christmas pudding had the most coins in it, and then I went, okay, that's my bit, and it's not even like a proper sort of hexagonal chart. I really carefully go dig out the bit with the coin. Right? You can see that is cheating, right? You can see that, and you can see that that's cheating in exactly the same way that it's cheating when you look under lots and lots and lots of different cups. So this is the problem of people doing unprespecified, dodgy subgroup analysis. So this is something you find in clinical trials fairly commonly. You do your trial, comes to the end of the day, you pack up, you analyse your data, turns out your treatment doesn't work overall, but maybe it works really well in Chinese women between the ages of 55 and 80. So that's your positive finding, you write it up, and suddenly it becomes the canonical treatment for that patient population. Now, this is sufficiently well recognised that it has been mocked in the medical literature for decades now. People continue to do it, but it's been mocked for decades, to the extent that there's this sort of small industry of people doing facetious epidemiology papers about it, right? So one classic is on heart attack patients. So it's literally a fake trial, right? They took 1,000 patients who came through, I think, 5 hospitals' A&E departments with heart attack, and they said, okay, we're going to simulate a trial. We're going to do an imaginary trial. So all the patients who come through, they're going to be allocated to treatment 1 or treatment 2. But neither treatment 1 nor treatment 2 existed. It was just like an imaginary label that was applied to these patients. All the patients just got best quality, standard of care, normal treatment. So then they collected all the follow-up data in this completely simulated trial, and then went, okay, let's see, if we really play fast and loose with how we analyse the data, can we make it look like treatment 1 is better than treatment 2? And yeah, they could. They found that there was obviously no difference in survival between the two groups, because they were both treated in the same way, and treatment 1 and treatment 2 did not exist. But in a subgroup of 397 patients, characterised by 3-vessel disease and abnormal left ventricular contraction, survival of treatment 1 patients was significantly different to treatment 2 patients. Right? Better than that, you can sometimes find even really nice biological gradients. So this is people who are getting a funny procedure to try and widen out their arteries when they're narrowing, and here overall, the treatment's reasonably effective. So, sorry, just to be clear, if the dots are further over to the right, that means it's really effective. If they're further over to the left, that means it's less effective or actively harmful. If the horizontal, if the blob and the horizontal line saying how big the treatment effect was touches the vertical line, the line of no effects, that means there's no statistically significant benefit or disadvantage either way. So this is the overall benefit for the whole population of people in the trial. Overall, you're better off getting this operation. But they went, oh, let's do some subgroup analyses. So they did this subgroup analysis, and look, you can see, right, I'm not going to tell you what the variable is yet, but you can see that, look, it's really interesting because people who've got not a lot of that variable, they actually, if anything, it's possible, maybe, it's not statistically significant, but maybe the treatment's actively harmful. And then as you get more and more of this thing, whatever this thing is it age? Is it blood pressure? Is it, I don't know, it's really height, BMI? I wonder what it is. So as you get more and more of it, it looks like the treatment becomes more and more beneficial. And it's month of birth. Isn't that nice? And if that had been a biologically plausible variable down there, then you would have been very inclined to go, God, actually, that's really interesting. We should do some confirmation studies on it. Actually, do you know what? Until we do that, I'm just going to apply that to my clinical practice anyway. The best example of this is the ISIS-2 study. I don't know how secret this is. Okay. An argument was had between the people involved in the ISIS study and the Lancet. So the ISIS-2 study on aspirin was one of the biggest and most important trials to be conducted at the time, a few decades ago. When it came to be published in the Lancet, there was a big argument, basically, and the journal said, look, this trial's so big, we'd like you to do, it's a great finding, it's great, and we're definitely going to publish it, but this trial's so big, let's do some subgroup analyses on it and see whether aspirin is particularly good or bad in different populations. And the researchers said, no, we don't have the statistical power for that. That would be a statistical fishing trip, and that's not okay, we're not going to do that. And the Lancet said, no, we really must have, we insist that you do some subgroup analyses on this data. And they said, no, we do not have enough patients in here. I know it looks big, but it's a rare outcome that we're measuring. We don't have the statistical power to do subgroups. And they said, well, we're not going to publish it unless you do some subgroup analysis. And they said, all right, fine. Aspirin works, but it doesn't work if you're Libra or Gemini. Happy now? Which I think is one of the all-time greatest passive-aggressive responses to reviewers' comments. So, next, external validity. All right. Sometimes people conduct trials in perfect patient populations that are so perfect that they're completely unrepresentative of the real world of patients. Now, this is very rarely justified on the grounds of practical value. So, asthma. Asthma is not a rare condition, right? It's about 1 in 12 adults. There's millions of people in the country with asthma. Now, really interesting paper went out and grabbed all of the trials that were used to create the asthma treatment guidelines that are most commonly used in the UK. So these are the trials that were used to make decisions about which treatment is best in asthma, and if you don't do well on that, then what's next in the decision tree, and so on. So these are trials which are being applied to an everyday population of over 5 million people. So then they went through and they looked at the inclusion and exclusion criteria of those trials. They took a representative sample of 200 patients, everyday patients from primary care, GP care in the UK, who had asthma, who were being treated with these guidelines, and they went, okay, overall, what proportion of those patients would have been eligible to participate in the trials that are being used to inform their care? And the answer was 6%. 6%. Now, there is no need for, it's not like it's hard to find asthma patients to participate in your trial, right? I would say there's probably, how many of you are, I don't know, 100 maybe? So there's going to be probably about 8 people in the room with asthma already. That's a pretty good start, right? It wouldn't take us that long. There is no excuse for this. And yet, that's what happens, because we've made the costs of trials, actually, is part of the problem, so spuriously high, often with spurious regulations that don't address substantive problems, but get in the way of doing cheap trials, that we've driven up the cost so high that people are desperate to get a good answer, or a significant answer, from the smallest possible number of patients in order to keep costs down, and so they are actively incentivised to put unrepresentative patients who are most likely to be positive responders to the treatment into the trial, which is foolish. Anyway, good God, these are terrible slides. Right, okay, here's an interesting one. How long have I been talking for? When do I stop? What time is it? 11:42. Another 5 minutes? Another 10 minutes? Is that including questions, though? Would that leave time for questions? So if I talk for 8 minutes, there's 10 minutes of questions? All right. All right, so this is interesting. If you have unrepresentative patients in your trial, that's a problem for, firstly, can you apply the results of that trial to real-world patients, right? If you have patients in your trial who've got no other medication, no other diseases, they're really healthy, they've just got one medical problem, and when you treat it, they're much more likely to get better. Can you then apply those findings to an elderly person living alone with lots of complex social and medical problems who's got 5 different diagnoses and is on 7 different drugs with a little bit of renal failure, right? I don't know. It's a real problem. But it also messes up your cost-effectiveness calculations. So this is a glorious piece of research on the cost-effectiveness calculation done by NICE for COXIBs. So COXIBs are another really, really interesting example of a drug which has some problems but also some benefits. So COXIBs are painkillers, and the idea of COXIBs is that they are less likely to cause gastric bleeding than old-fashioned cheap painkillers like ibuprofen. Now, they've got a very bad reputation because it turns out they also make you more likely to have a heart attack, which is unfortunate. And it is unfortunate. Actually, I think it's quite interestingly. I think they clearly have value. If you're treating a patient who's at high risk of gastric ulcers and high risk of gastric bleeding, then it actually makes a lot of sense to use COXIB. And I would say the fact that the company were caught red-handed, one company in particular, were caught red-handed, really trying to obfuscate on the heart attack risk, made that heart attack risk so salient in people's minds that actually perversely it probably stopped people using COXIBs in some situations where they would have been appropriate to use. It's a strange, strange business. You know, there's no such thing as good and bad drugs, really. There are just good and bad decisions and good and bad evidence on individual trials and individual patients. But the price of COXIBs was they're quite expensive, but they reduce your chances of having a nasty bleed. So, NICE, it's their job to go, all right, is this a cost-effective thing for the NHS to prescribe? So to decide that, you've got to work out how much money do you have to spend in order to prevent one bleed, right? So if you want to do that, then you take the data from the trials, you go, okay, in these trials, 50 out of every 1,000 people had a bleed in these trials on COXIBs. But the people on COXIBs had half as many bleeds. So that's only 25 out of every 1,000 people on COXIB had a bleed. Now, if you're trying to work out the cost of preventing a bleed, it's very simple. You go, all right, there's 1,000 people on COXIBs to prevent 25 bleeds. So that's $500 per patient on COXIBs. So for spending $500,000, you prevent 25 bleeds. So each bleed costs about $20,000 to prevent. Therefore, this is an okay thing to spend money on, right? And you get that, yeah? So you can now become health economist and go and work for the National Institute of Health and Clinical Excellence. But the patients in trials were much more likely to have bleeds. And that's because if you've got a treatment where you're trying to show, stop looking at the slides and listen, this is difficult. If you've got, if you're doing a trial where you're trying to prevent bleeds, you want to do it in a smaller number of participants as possible, because every extra participant you add to your trial will cost you $10,000, maybe $20,000, right? So you want to keep the numbers down. Now you're trying to detect a difference in the number of bleeds between the people getting your expensive new COXIB versus people getting old-fashioned naproxen or old-fashioned ibuprofen. In order to be able to detect a difference in the number of bleeds, the best way of doing that is to enrich your population with people who are at really high risk of having bleeds. Because the more bleeds you have per participant, the fewer participants you need overall to detect a difference in the number of bleeds. You can see that, right? Now, that's fine to an extent as far as it goes. It means that the findings aren't necessarily generalizable to people who are at lower risk of bleeds, but I can see why you've done it. What's interesting is when NICE use that for their cost-effectiveness calculations, because meanwhile in the real world, and this is Ched Van Staar, who's awesome, who I've done stuff with, he's amazing, so he went and grabbed the GP data and just went, okay, let's look at the bleeding rate among people in GP care in the UK who actually get coxibs. And overall he found, when you just look, you see that on average, the kind of people who get coxibs in the UK have about 10 bleeds out of every 1,000 patients, and so that goes down to about 5 bleeds out of every 1,000 if you're on coxibs. So that means now you have to have 1,000 people on coxibs to prevent 5 bleeds. Previously, 1,000 people on coxibs prevented 25 bleeds because this was a really enriched. But in the real world, you have to have 1,000 people on coxibs to prevent 5 bleeds. You can see why, yeah? Yeah? Isn't it interesting that you get that and nice don't? Anyway, so $500 per person on coxibs, so that's, now you're paying $500,000, the same amount, but you're only preventing 5 bleeds. So now suddenly there are $100,000 per prevented bleeds. Isn't that interesting? Isn't that clever? And isn't that amazing that NICE didn't notice? Anyway, next, you can do trials that are too small. You can do trials that measure surrogate outcomes. How long have I got? What's the time? 11:48. Okay, surrogate outcomes. So, okay, the All Hat trial, probably the biggest, most expensive trial pretty much ever done. It's well over $300 million. It was a big trial following people up for a long, long, long time, like 7 years. And it was comparing different blood pressure drugs against each other, different lipid-lowering strategies against each other, and it was measuring death as an outcome. And the idea was, you know, we measure surrogate outcomes like blood tests or blood pressure or whatever, but actually we need to make sure that when we find that a treatment is lowering these laboratory measures, it's also having a really good impact on real-world outcomes. And this is important because we've been caught out before. So the CAST trial, for example, which was on treatments to prevent abnormal heart rhythms after you've had a heart attack, found that the class of antiarrhythmic drugs that we were using were very good at reducing the frequency of abnormal heart rhythms in patients, and so everybody was using them because we measured those in trials, and we said, well, that, you know, people who are having abnormal heart rhythms, they're at increased risk of dropping dead, and so if we've got something that reduces the rate of abnormal heart rhythms, that's got to be good. The CAST trial, we finally did a trial that measured real-world outcomes, death. People talk about patient-oriented outcomes that matter. I would say death. Basically, the most patient-oriented outcome, it really matters. When they finally measured death in the CAST trial, they found that these drugs did indeed reduce the rate of abnormal heart rhythms, but they actively increased your chances of death. Everybody was very surprised, very alarmed, and we stopped using them very quickly. The All Hat trial, another really interesting example. 2 drugs, one fabulous whiz-bang expensive new blood pressure drug made by Pfizer, one boring old-fashioned cheap blood pressure drug that had been on the market forever and was now cheap as chips. They were both equally good at lowering blood pressure. For various reasons, Pfizer thought that their new drug was going to be better than the old drug at lowering blood pressure, so they really wanted to put it in this trial. They put over $100 million into the trial fund in order to add their drug onto this trial that was already set up and about to run. An extraordinary gamble, and they couldn't possibly have known, this isn't a criticism in any way, in fact it's great that they did a trial measuring real-world outcomes, but the trial had to be stopped early on ethical grounds because people getting the new drug were dying so much faster than people on the old drug. Now it's really important to understand what that means, because that doesn't mean that this drug was a killer. It doesn't mean that it was actively slaughtering people. It doesn't mean that you'd have been better off taking nothing. It had to be stopped because it wasn't as good as the best currently available treatment, which is exactly what we came across in the first slide, right, where we saw that actually being better than nothing isn't good enough. We need good quality evidence measuring real-world outcomes from fair tests to show us which treatment is best in representative real-world patients. And that's not what we have enough of today. We've been too permissive in medicine. We've been too accepting of mediocre research, and there is no need. Thank you very much.
Thanks, Ben. We've got time for about 2 or 3 questions. That gentleman there went first. And then we'll go in.
The new policy to make patient records available on a national basis.